Hi, today I'll be showing a script written in Matlab to interact with the task of Flac. The script or the study I'm presenting here is a column of sand, and we are trying to discover its natural frequency. So the mm, the dynamic action imposed in Flac is a sinusoidal wave is based on a sinusoidal wave, and basically, MATLAB would change the frequency of this wave from 1 to 30, basically, and it has this look. So we'll go in steps from 1 to 30. The MATLAB script has this look. So we'll start from the main folder in the task of flag, and then every time the script will open this text file called frequency, which only has a number. It can be 1, 2, 3, and until the 30 hertz as defined in FLAC, because we have this variable here going from going from steps of 1 until 30. It could be the steps could be even lower, but for this case it really doesn't matter. So the software then will import certain history files from generated by FLAC. These are displacements across the sand column, and we'll use this to assess the the relative displacement, and with that we can discover the natural frequency of the sand column in this case. So this is just the way to calculate the relative displacement. Every time uh, we'll use a point and subtract the um, the displacement occurred at the base. The thing here is that we have to pick up the same point in time. So this is the tricky part of the script. But that's solved. Then uh, FLAC will, the MATLAB will save all the files into a folder. We'll move the files to a folder, and then we'll delete the, we'll not delete, sorry, but we'll start all over again the calculation. So the script in FLAC has this look. It's just a normal linear constitutive model for the sand with where we define the density, the bulk modulus, and the shear modulus, and we have 11 layers. So actually, I can show the look of the problem if I go here, import record, and then this one, and if I press yes to execute, wait, sorry, rebuild, I mean, and then the software will start, and I can refresh my plot, and here it is, column of sand. So this is a typical 1G problem. So in this case, we don't want to use the graphical interface. We have prepared, I'll quit the software. So in um, in MATLAB, by using this command, you can open, basically, I'll just clear all. By using this command, you can open a FLAC window. And since it has already FLAC ini file prepared, so as soon as I launch or open FLAC, it will immediately open this file, which is basically the file with all the commands to be set in FLAC. So without further ado, let's start. I'll start the so all the results that I want to get will be saved in a specific file. So if I press run, then immediately Matlab launches Flac, and then it starts running. So as we can see, it's starting now with a frequency of 1. So this takes a little bit of time for each frequency. The problem time as defined in the software is, if I recall correctly, we have set um, 7 seconds, which is also the as defined here in Excel, the action imposed. So this is already almost finishing. So now Flac is creating all the files as required. Of course, I'm just looking at the displacement. We actually are generating much more files. We have accelerations, shear modulus, so we can do a lot of analysis or post-processing of the data. And with MATLAB helping doing that, this is way easier than going in Itasca Flac and generating the plots and then doing the analysis. So this will generate roughly, I think we have 185. Okay, so 85 is 3. So almost finishing. So then MATLAB will close Flac if everything goes accordingly. And then it will save all the Flac files into a folder with the frequency number. So we will get 30 folders by the end of it. So now I have the max displacement at the top. So this is below millimeter because it's elevated to minus 0.4. And now the the Flac closed and opened again. And if I go and check what is the frequency now, I already have a notice here that the file was modified, and I'll just reload it. And now I can see that the frequency file has 2 Hz. So this is what Flac is using. So, and also now I have a folder here called is results, and basically I already have for 1 Hz I have the 6.21 elevated to minus 0.4. So this is below millimeter. So I'll just show what will happen now. Also, as you can see now, I'm in the folder. I have the files being generated, and the previous files for the frequency of 1 Hz is already saved here. So of course I could go and get the coffee because this takes a lot of time. And if uh, here I could actually just write around 7 files, and I would have the information I need um, for this example basically. But yeah, I haven't changed the original file, so that's the reason why I still have all these 85 files being generated. Just to show you how a file looks with the results from MATLAB. So I have the dynamic time, and then this is the average of the shear force in so X and Y. So this is what we call distortion. And again, I'm getting the call, and the frequency was updated in MATLAB, again generated. So here already have a change in the displacement due to the change in the frequency. So now that the calculations have ended by reaching the frequency of 30 Hz, we'll go to the FLAC folder and check the results, which are stored together with all the calculations folders. So here, if I copy this to, and I'll open Excel, and I will have my results. Now, this is frequency in or F in Hertz, and this is displacement in millimeters. So if I sorry, this is in meters. So I need to, if I want this in millimeters, I need to multiply this by 1000. Wait. And now I have in millimeters. That makes more sense. Okay, so I'll do a graph. Select data, head, and for the X, I'll have the frequency, and for the Y, I'll have the displacement. And as we can see, here is the peak. We have it, so for this sand layer, the natural frequency, it's located around 23 Hertz. So I hope you enjoyed this MATLAB Flac interaction. Until the next time, take care.